So basically in today's assignment we'll be discussing about a few problems on electrostatics, mainly Gauss's law and things like that. So I'm sure you guys must have been taught Gauss's law in one of your courses recently or also in the NPTEL course. So these problems are mainly based on Gauss's law and some other things in electrostatics which you may come across if you haven't till yet. So the first problem here, it says that there is a finite sheet in the xy plane going from 0 less than x less than equal to 1 and 0 less than equal to y less than equal to 1, and the plane has a charge density of rho s which is given by this formula.
Sir?
Yes?
Hello?
Hello? Yes?
Hello, sir?
Yes, I can hear you.
Sir,
Tell me.
excuse me.
Yes?
Hello?
Hello?
Sir, it is not visible. Screen is shared, but sir, your screen is shared, but the problem is not visible, sir.
Okay, there is a network problem here. It's trying to reconnect, it's showing.
Hello? Share.
Hello?
Hello?
Yeah, there is a network problem actually.
Hello?
Hello?
Okay, sir.
Hello, am I audible now? Hello, am I audible here?
Yes, sir.
Okay, alright. I'm sorry, I had lost my connection at that time. I'll reshare my screen and go ahead with the presentation. You guys can see my screen, right?
Yes, sir.
Alright. So, the first question, it states that there is a finite sheet in the xy plane going from 0 to 1 and y going from 0 to 1 on the z equal to 0 plane. Okay, and there is a charge density of rho s equal to given by this formula on that sheet.
Excuse me, sir.
Yeah.
Excuse me, sir.
Yes.
Can you zoom it?
Okay, it's too small.
Now, okay, sir.
I'm sorry. Okay. Is this fine? Okay.
Now it's okay, sir.
All right. All right. So I'm given a charge density of this formula on this particular finite sheet over here, and I'm told to find what is the total charge on the sheet. So can anybody tell me how to proceed with this problem?
So we need to take surface integral.
Yes, exactly. And what is that surface? It's on the xy plane, right?
Yes, sir.
Okay. So the integral is shown over here. So this is my total charge density, and so the total charge on the surface, as she said, is this charge density and the surface integral of this. So basically charge per unit area multiplied by area gives me the total charge. So are all of you familiar with double integrals, like a surface integral?
Yes, sir.
If anybody is not familiar, then I can help them with this problem. I can go through the solution. Okay. So basically you substitute x square and y square like this in this particular equation, and then for basically a double integral you do the integral separately over the two variables. So first I do this integral over the q variable, and the result which I get is in terms of the p variable, and then I do this integral over the p variable again, and both the variables go from 0 to 1 as per the boundary conditions given in the problem. And if I do that, I get the total charge on that particular charge sheet. Okay. So moving on to the next question. So for that given charge sheet, what is the electric field at the point 005? So can anybody tell me how to proceed with this one? Yes. So how do I find the electric field at point 005, given that I have a charge sheet in the xy plane going from 0 to 1? Okay, so let me explain this part then. So you all are familiar with the electric field due to a point charge, right?
Yes, sir.
Okay. So the electric field due to point charge is basically 1 by 4 pi epsilon naught into the charge divided by the square of the distance of the point from the charge, right? So right now we have a sheet instead of a point charge. So what we can do is that we can consider the sheet to be made up of an infinite number of point charges. Okay. So then what we do is that basically we calculate the electric field at point P due to each and every one of these infinite number of point charges and add them up. So basically we have to do an integral over all these small contributions to get the entire electric field. Is this part clear? What I said right now? Yes? No? Alright.
Yes, sir.
Alright. So what I do is that I take a very small area, like an infinitesimal area dA equal to dx into dy, where dx and dy are very small. And the coordinates of this area are x comma y comma 0. It's an area on that charge plane. Okay. Then the position vector from this area to point P is given by this. So basically this minus this gives you the position vector r. Okay. So then the electric field due to this infinitesimal area. So this infinitesimal area I'm considering as a point charge. So the electric field due to that will be 1 by 4 pi epsilon naught into charge density into area, which gives me that particular value of the charge, divided by r cube into r vector. So this is the electric field due to the infinitesimal area, and if I do an integral over this electric field over the entire area of the sheet, I get the total electric field. Okay. Clear? Yes, no, maybe. Or if you have any doubts, you can ask me directly. All right. So what we do is that we are given the value of rho s over here. So rho s is xy into this quantity, and we have already found r. So we substitute these things, and then we have many double integrals over different components of the vector. And finally we get this particular value of the electric field. So this is given in units of nanocoulomb per meter square, this quantity within brackets. So in order to convert it into SI units, we multiply it with 10 to the power 9 minus 9. Yes, and then we get this particular value of the electric field in terms of SI units. Okay, so the question after this is that what is the force experienced by a minus 1 millicoulomb charge located at 005? So we know that the force is the electric field multiplied by the charge located at that point. So I know that my charge is 1 millicoulomb. So I multiply with the electric field which I obtained in question 2, and then I get the force in terms of units of millinewton. So this is the force. So I hope this question is clear with everybody. Yes? Any doubts or questions?
Yes, sir.
Okay. So the next question,
Yes, clear, sir.
yes, it's clear, okay. All right. So this question 4 on 5, this one is based on Gauss's law. So are you all familiar with Gauss's law? Yes or no?
Yes, sir.
All right. So Gauss's law basically states that if you are given an enclosed volume and you have some charge within the volume, then the electric flux through the surface enclosing that volume, it is equal to the total charge enclosed within the volume divided by epsilon naught. So that is basically Gauss's law. So what do we have here? Here we have a charge distribution which has a spherical symmetry, meaning that it depends only on the radial coordinate r. It has no dependence on theta or phi if you use spherical polar coordinates. Okay. So a charge distribution with a spherical symmetry has this charge density which is given by rho of v, and this charge density is valid between 0 less than small r less than capital R. So what is the electric field for any r less than capital R? So then we use Gauss's law over here. So like I said, Gauss's law, this is the electric flux of the electric field due to through a closed surface S. So this is my surface, or I can consider this to be my surface as well. So there is a net flux of electric field passing through the surface because of all the charges which are enclosed within the surface. And so this flux is basically given by the enclosed charge, which is Q subscript ENC, Q enclosed, divided by epsilon naught. Okay. So here the in this problem we have the surface of a sphere, and we are asked that what is the electric field at small r, which is less than that, which is less than capital R. So from the symmetry of the problem, since the charge distribution which is given by rho of v, since my charge distribution itself is has a spherical symmetry, so that means the electric field which encloses this charge, it will always be in the radial direction. It cannot have a theta or a phi dependence, right? Because rho of v does not have a theta or a phi dependence. Alright. So in that case, my electric field will be in the radial direction. So that is why E is E into r cap. And similarly, my area element, so my Gaussian surface is a sphere, and the normal vector to the surface of the sphere is also in the radial direction, right? So my normal vector to the sphere, it is also in the radial direction. So both my electric field as well as the normal vector to the surface are in the same direction. So basically a dot product between them is simply a multiplication of their magnitudes. So is this portion clear? How E dot dA is equal to E into 4 pi r square? Yes, or should I repeat once again?
Yes, sir.
Alright.
Please repeat, sir.
Okay, I'll repeat it once again. So what we have to find is E dot dA, the dot product of E and the area element, okay. E dot dA is basically the flux of the electric field passing through the surface of a sphere of radius r, because here my Gaussian surface is a sphere, because my charge distribution has a spherical symmetry. Okay, so since my charge distribution has a spherical symmetry, this electric field, it will only depend on, it will only be in the radial direction. It cannot have a phi or a theta component. It will only depend on r, right?
Yes, sir.
Okay, and the area vector, so dA is basically a normal to the surface of my sphere. Now if my sphere is centered at the origin, then the normal to the surface of this sphere will always be in the radial direction, right? Yes.
Yes, sir.
Okay, so both my electric field at the surface of the sphere and the normal vector are in the same direction. So their dot product is basically a product of their magnitudes, right?
Yes, sir.
Okay, so then
Yes, sir.
this surface integral of E dot dA, it is basically E into 4 pi r square, where 4 pi r square is obtained by integrating dA over the entire surface area. So basically this is the surface area of the sphere of radius small r, right?
Right, sir.
Okay, so I have my left hand side. Now what is given in my right hand side? Right hand side is the charge enclosed within the sphere of radius small r divided by epsilon naught. So in order to find the charge enclosed within the sphere of radius small r, we integrate the charge density over this volume of the sphere. Alright, so if I do a volume integral of the charge density over a sphere of radius small r, I get this value, right?
Sir, how come we are talking about volume integral, but we have taken uh, simple integral, sir?
Okay, so over here I had skipped a step actually. So basically Q enclosed is an integral of the charge density over the volume. Now what is a volume integral? A volume integral is basically three integrals over an infinitesimal volume. In spherical polar coordinates, that volume is r sine squared theta d phi dr, right?
Yes, sir.
Okay, now if I do the integral over theta and phi, so phi goes from 0 to 2 pi, so integral of d phi will give me 2 pi, right? And
Okay, sir.
Yes, sir.
and integral over sine theta, okay, integral over sine theta from 0 to pi by 2, oh sorry, 0 to pi, so that will give me a value of 2, right?
Yes, sir.
So 2 into 2 pi, I get 4 pi, so this is my 4 pi here, and r square is the r integral which I am about to do now.
Okay, sir.
Okay, alright. So after doing the theta and phi integral, I do the r integral over here and I get this particular value of the charge enclosed. Okay, so if I equate my left hand side and right hand side, so my left hand side was E into 4 pi r square and the right hand side is the charge enclosed by epsilon naught. So I get this value of the electric field for r less than capital R. Okay. So the next question, it states that my charge density is 0 for small r greater than capital R. Then what is the electric field at some radius small r greater than capital R? Okay. So the left hand side remains unchanged because I am simply expanding my Gaussian surface to a radius small r greater than capital R. So my left hand side remains E into 4 pi small r square. Okay. what happens is that my right hand side changes, the charge enclosed changes. So what will be the charge enclosed now? So the answer is simple one. Since there is no charge outside a radius capital R, so even if my surface has a radius of which is sorry, so since there is no charge outside my sphere, so even if my spherical Gaussian surface has a radius larger than that of the sphere, then it is not enclosing any extra charge, right?
Yes, sir.
Okay, so then the total charge which is enclosed by my new Gaussian surface is basically the entire charge contained within the sphere of radius capital R, right? So then what I do is that I basically integrate from 0 to capital R to find the total enclosed charge. Clear?
Yes, sir.
Yes, sir.
Alright. So if I do this integration, I get my value of the total enclosed charge, and from that I can calculate the electric field. So I get this answer. So this question is clear, right? If anybody has any doubts or queries, you can ask me directly. Okay, so assuming that there are no doubts or queries with this question, we go ahead with the next one. Which of the following is 0? So can anybody tell me which of the following are 0 over here?
So can you please repeat the question, sir?
Okay, can you see my screen? It's given over here. Which of question number 6? Which of the following quantities is 0? Gradient of divergence, or divergence of gradient, or curl, or curl of gradient?
Curl of gradient
Why
or
do
divergence of curl.
Okay, why do you think that curl of gradient is 0?
Here, if you find the gradient,
Huh?
you will get a vector, no?
Yes.
And when you take the curl of that vector,
Yes.
I think it is going to be 0.
But
I cross I, J cross J.
no, but those vectors can have other components like the curl vector and the gradient
We
vector.
will get other components, right?
Uh-huh. So that won't be 0. So then which is the correct answer here? Last option is not correct.
Come again, sir.
So curl of gradient is not 0 in general. So
In general, not 0, sir,
okay.
actually.
So which
But
is
options, in the options, there is no other choice.
yes, in special cases it can be 0, but for every case there is one of these four quantities which is 0 in general. So which is the quantity?
The voice is not clear, sir.
Voice is not audible.
Not audible, sir.
Can you hear me now? Hello?
Sir, it's okay, sir. Voice is okay.
Okay, okay. So which of these four quantities are 0? So the answer will be curl of curl. Why? Because if you have a cross product of two same vectors, that is 0, right? A cross A is 0. So that is the same reason why curl of curl is also 0. If you see, if you take curl of a particular vector, then all components will cancel out. That is why for any vector, curl of curl is always 0.
Yes, yes, sir. Yes.
Okay. All right.
So what could be the answer, sir?
Answer is curl of curl. This
Only curl of curl.
Yes, because none of the above are zero unless in special cases. So
Okay,
curl
sir.
of curl is always zero.
Okay, sir. Okay.
Hmm.
So these others can be zero sometimes.
Yeah, sometimes it can be zero, special cases, but not always.
Oh. So can you give any examples, sir?
For example, gradient of divergence. Or let me take a divergence of gradient. So this is basically your Laplacian.
Laplacian. Okay.
Okay. So
Yes, sir. Laplacian.
yeah, so you know the Poisson's equation.
Equipotential surfaces.
Exactly, exactly. All equipotential surfaces, the Laplacian is of the potential is zero.
Laplacian is going to be zero.
Yes, like that. But if the surface is not equipotential, Laplacian won't be zero.
Okay. And this, sir, this curl of gradient.
Curl of gradient of a vector you can consider.
Yes, sir.
I mean, right now I'm
Del
not.
cross.
For
Del
example,
cross.
yeah. For example, if you have which a field which is not electrostatic,
Okay. Yes,
so then
yes.
curl of
If it
E,
is not
yeah, curl of E is not zero in that case. And
curl of E not zero. Okay. Yeah. Yes, yes.
right. All
Okay,
right.
sir. Thank you.
Okay. So what about Gauss's theorem is correct? Okay. So the seventh question is, uh, which one of the following is correct about Gauss's theorem? So the correct answer is that Gauss's theorem is applicable in gravitation.
Cannot be derived by. What about Gauss theorem is correct?
Hmm.
Okay. Is not valid for conservative fields obey mass square.
So the correct option is D because it can be derived from Coulomb's. It cannot. The first option is that it cannot be derived using Coulomb's law, but that is incorrect. From Coulomb's law only we can derive Gauss's theorem, and it is valid for conservative fields as well. So the correct
Yes,
answer
sir.
is that is applicable in gravitation.
In electrostatics, electric field is conservative.
Yes, yes, right.
So Gauss law is applied there.
So this option is not correct. That it is not valid for conservative fields.
Third one is, sir. Third one.
Yeah, third one is the correct option. There is a Gauss's law
But
for
the nature of force is both are same, sir. Electric force and gravitational force. Nature is same.
one is an inverse square law. The other one
Sir.
is yes, it goes as 1 by r, I think, gravitation.
Hmm.
But then
But
again,
there is no repulsion, I think, in that gravitation.
no, there is no repulsion over there.
Okay, here there is a repulsion.
Yes, yes. So basically, in gravitation, instead of the charge enclosed, you would have mass enclosed. So a mass enclosed within a Gauss's surface would apply some sort of gravitational field at some distance from it. So that is basically Gauss's law in gravitation.
Okay.
Okay. Question number 8. Divergence theorem is based on which of the following?
Divergence.
So,
Gauss law can be applied divergence theorem.
hmm.
Stokes contains curl, sir. Curl, no?
Yeah, Stokes' law contains curl. So that is curl of a vector is
This
equal to
Ampere's law is also
Ampere's
curl
law
only.
comes from Stokes' law basically.
Yes.
So divergence theorem is basically a theorem, okay? So it cannot be derived from some law. It is a theorem of mathematics.
Okay.
Alright. So it is not derivable from any of them. So the correct option is none of these over here.
None of these, yes.
So is this clear to everybody? These questions 6, 7, 8. Okay, so that is clear. Moving on to the next question, that is question 9. So, which one of the following is not correct?
Gaussian surface for a line charge.
Others can also answer if you want. Yes, can anybody tell me which one is not correct and why it is not correct?
I think option 3, sir. Gaussian surface for a point charge will be a cube.
Okay, so that is given as an accepted answer over here, but technically speaking, um,
See here, line charge. If you take the line charge,
mhm,
so one can easily draw a cylinder.
yes,
And for point charge also, in order to get the symmetry, we
yes,
can draw sphere.
yes,
Coming to point charge only, cube only,
uh,
uh, Gaussian surface. One can draw, I think, sir. Cube.
okay, so what is
Right.
that? All right, I
Well,
see.
because the cube also having symmetry.
Yes, so symmetry is the next question. So, what is a Gaussian surface? A Gaussian
Gaussian.
surface should be a surface which encloses the charge, right?
Yes.
It should
Yes.
not have any holes. That is an important property, because if it has holes, then the electric field can penetrate through multiple points on the Gaussian surface. So that won't be a correct Gaussian surface for that particular electric field configuration. Yes, Vanaja, you have a question? Okay.
Can you repeat it, sir?
Yes. So a Gaussian surface, the property of a Gaussian surface is that it should enclose the entire charge. Alright. And it cannot have the electric field lines passing through the surface more than once. So in some sense, a Gaussian surface cannot have holes, or it cannot have a U-shaped structure, because if it has a U shape, then, for example, I'm just giving U shape as an example. If it has a U shape, then electric field can pass through it more than once. So that won't be a Gaussian surface, right?
Yes, sir. Okay.
All right. So now coming back to
That
these
means
examples.
through two limbs of U shape, sir.
Yeah, yeah,
Okay.
right,
Okay.
Yes,
right.
now it's clear. Okay.
Yeah. So that won't be a Gaussian surface because the electric field intersects multiple times through that.
Okay. Okay.
Okay. But if you look at the three cases over here, for a line charge, it is a cylinder which encloses the line. Perfect Gaussian surface. Yes. For a sphere
Yes, sir.
also, it is a, for a point charge it can be a sphere. But then again, for a point charge, even a cube will be a Gaussian surface if you think of it, because it encloses the charge and electric field lines pass through that surface only once. So electric field is properly defined at every point on that surface. So technically speaking, all of these cases, the Gaussian surfaces are correct. I mean, all of these cases are actually valid Gaussian surfaces. Now the question is that while solving a problem, what kind of Gaussian surface will you take? You will take a Gaussian surface that matches with the symmetry of the problem in order to find the solution in the most easiest way, right?
Yes, sir. Yes.
So that is why when we take a point charge, we always take the Gaussian surface to be a sphere because of the spherical symmetry. Because if we try to
Yes.
calculate a field for a point charge using a cube, calculation will be difficult but not impossible. Okay, so I guess this question is clear about Gaussian surfaces.
Yes, sir.
Alright,
Yeah.
okay. So the last question is that what is the electric field due to an infinitely long straight uniformly charged wire at a distance d? Okay, so this is, we have a uniform wire of infinite length, and we have to find the electric field at this point, which is at a distance, say, d from the wire, which is w. So over here, since from the symmetry of the problem, we can consider a Gaussian surface which looks like a cylinder, a cylindrical Gaussian surface, right? So the Gaussian surface here is a cylinder of length L and radius r, such that the surface penetrates the point P at which I am going to calculate the electric field. Okay. So from the symmetry of this problem, we know that the electric field at some distance from the wire, it is always in the radial direction, right? The electric field is always radially outwards from the wire, because this wire has a uniform charge. Okay. Okay, if that is clear, then the electric field is directed in the radially outward direction, and the curved surface area is basically 2 pi r, which is the circumference, into the length of the cylinder. So the curved surface area is 2 pi r into L. So from Gauss's law, the left hand side is basically the electric field into the curved surface area, which is E into A. Now the right hand side is the charge enclosed by this Gaussian surface. Okay, so since this cylinder has a length L, and we consider lambda to be the charge per unit length on this wire, basically the linear charge density. So what will be the charge enclosed within a length L if lambda is my charge per unit length?
QL, sir.
Lambda into L, because lambda is the charge per unit length. Charge per unit length
lambda.
into length. So lambda into L is the total charge enclosed within my Gaussian surface, which is a cylinder of length L.
So actually we will take lambda is approximately equal to Q into L, sir.
No, actually, Q is lambda into L, because Q is the total charge that is enclosed. Lambda is the charge per unit length. Okay.
Yes, sir. Yes.
Okay. So my charge enclosed is lambda.
Instead of surface, it is sigma times ds.
Yes, yes. So that is charge per unit area into area, or charge per unit volume into volume,
sir,
like
yes.
that.
Okay, rho times d tau.
Right, right. Yes.
Okay, sir.
So over here it is lambda into L. So I substitute lambda into L in place of enclosed charge, and so I get my electric field going as lambda by 2 pi epsilon naught into R. So what is the electric field at distance d? I substitute R equal to d, and then I get electric field is proportional to 1 by d. Okay.
Yes, sir. Yes.
Okay. So I guess this is clear to everybody. So these were all the questions which I had to discuss. So if there are any extra things you need to clarify, or you want to clarify with me, you can go ahead. Or if there are other things you want me to discuss, then we have like around 10 more minutes.
Sir, I missed the last class also.
Okay.
So can you please share the assignments of the last class and this assignment, please?
Yes, yes. So we are uploading the assignments to a given folder. So NPTEL team has access to that. We'll tell them to share it with you, or you can request them to share it with you.
So sorry, you were not audible, sir. Can you please repeat what you
So we have been uploading these assignments to a folder given by the NPTEL team. So if you want, you can ask them to share these with you, or we can also ask them to share these with you. Either way.
Yeah, please, sir, please.
Alright,
Please.
we'll do that. Yeah.
Thank you.
Um, Anything else regarding whatever has been covered?
Sir, other than this, I have a problem, sir.
Okay.
When we take the cube, sir,
Uh,
all the charges are situated at all 8 corners, sir.
um, no, it depends on your configuration. Like, um, for example, where do
First,
you want the charges?
sir, all the charges are located at 8 corners of the cube, sir.
Okay.
Then how we will find the electric field, sir? For the
Okay, for that configuration you're saying.
yes, sir.
Okay, okay. So, what you can do is that you can consider multiple Gaussian surfaces. I mean, you can take a larger cube as a Gaussian surface. And then the total charge enclosed will be the all 8 charges, right?
Yes, sir.
Okay. So, at what point do you want to find the field? That is the question.
Uh, inside, sir, inside the cube at the uh, center, sir.
Oh,
At the center.
if you want to find it inside the cube, then you can simply sum over those 8 charges.
That's it. That's enough,
Yeah,
sir.
yeah, that is enough. Like, for this, you don't need to consider Gauss's law and things like that. Because
Okay.
if you look at it, if you have all the same charges at the 8 corners, then the field at the center will be 0 from symmetry.
Yes, sir. Yes.
Because field from every opposite pair will cancel each other out.
Okay. Okay. Sir, what is the difference between spherical shell, hollow sphere, and uniformly charged sphere, sir? These words are confusing little bit.
I see. So, uniformly charged sphere, let me start with that. So, you have a sphere, and suppose
Yes, sir.
you put charges all over the, I mean, you fill the sphere with charges uniformly. Okay.
Means outer surface, sir,
Inside,
inside,
inside the
every,
entire space is filled with charges of uniform density, rho. Okay. So then the
okay,
total charge within the sphere will be rho into volume, because rho is uniform and volume is 4 pi r cube.
okay, sir.
Okay, so that is a uniformly charged sphere. Now
Okay.
coming to a spherical, what was the second one?
Shell,
Spherical shell.
spherical shell.
Okay, so the spherical shell, it has basically a thickness. So inside the thickness it is hollow, but it has a finite thickness, unlike a uniform sphere which has a single surface, right?
Okay.
So a spherical shell will have an inner radius and an outer radius.
Inner and outer. Okay.
Because of the two surfaces. So you can have charges anywhere. You can have charge between also. You can have charge inside the spherical shell also.
Okay.
Okay.
That's somewhat confusing, sir, for me
Yes,
to
yes.
imagine.
Uh-huh. And what was the last one you were saying?
Hollow means hollow sphere.
Hollow sphere is basically you have nothing inside.
Nothing inside, just only outer ring.
Yeah,
Outer
only the
surface.
outer surface is there.
For that, inside electric field is 0.
Yes, definitely, because there is no charge
For
inside.
all bodies inside electric field is 0, no, sir?
Not always, because if you have a uniformly charged sphere, okay, so inside you can consider a Gaussian surface to be a smaller sphere, and that Gaussian surface will have a finite charge, right? It will enclose a finite amount of charge. So because of that enclosed charge, the electric field won't be 0.
Okay. Okay.
Now on the other hand, if you have a spherical shell whose interior has no charge and you want to find the electric field in the interior, that will be 0, because then your Gaussian surface is not going to enclose any charge.
Yes, yes, that is the first condition. Okay, sir. That should be fulfilled. Okay.
Yes, yes. All right. So, any other questions? Okay, if there are no more questions, then we can stop the meeting and we can meet again next Tuesday, same time.
Thank you, sir.
All right. Thanks. Bye.
Thank you, sir.